So it's my pleasure today to welcome our speaker for the colloquium, the first colloquium of the year at EVF. And we have here today with us Professor Charlotte Goetz, who is from Northumbria University. So in the northern part of England, some of you might be familiar with the university. It's a very up and coming. The group is like large and becoming larger and larger with lots of positions all the time. And so Charlotte did a PhD. Actually, we met 10 years ago, I think, when she was doing a PhD on the Rosetta mission. She was part of the magnetometer team on Rosetta at the TU Braunschweig. And she was doing a PhD with Karl-Heinz Glasmayer. And she got it in 2019. After that, she decided to move to the European Space Agency for 3 years, where she continued to study comets and do a lot of work, actually diamagnetic cavities, the subject of today as well. The Rosetta mission was like such a fantastic mission. We had like so many young people, starting, so many incredible scientists, like many generations. And we were really kind of a fantastic team. And Charlotte was a big part of that being fantastic. So we had a great time together, and now she got like a permanent position at the university in England, and that means that she is a professor. So she went through all the stages, and I could see that it was actually quite fantastic. So we're pleased today to actually listen to her talk about diamagnetic cavities. What are they? You might not know what they are. But this is quite an interesting thing, and maybe we don't actually know what they are still. So it's been a lot of observations for 2 years for the mission of Rosetta, and now Rosetta has been technically off since 2016, but we still continue to work on these incredible data sets as well. So Charlotte, the floor is yours. Just enjoy, and please don't hesitate to ask questions. And have fun.
Yeah. I hope this works now. And on. Okay. Yes. Thank you for the very kind introduction. There were so many nice people on Rosetta. It was just such a joy to be in, and I'm very glad I'm still working on it. So let's jump in. This is my title. I'm going to talk about the diamagnetic cavity at comets, and my frustration that we still don't understand it, really, even though it's been 9 years since we got this fantastic data set. I know that this is a comet, huh? Yes, everyone's seen one, hopefully. I thought I'd give a short intro at first for those that don't look at magnetic field data all day. And then I'll explain what is the diamagnetic cavity as much as we understand it. And then I will actually show some recent-ish studies that we do understand, because you always have to end on a high note, I think. Right, so what is a comet? So for those that don't like magnetic fields, I think these are the only actual telescopic observations that I have in this talk, so enjoy them. Yes. Okay, so this is comet 67P, Churyumov-Gerasimenko. This is the target of the Rosetta spacecraft. It's about 4 kilometers in diameter. All comets have that kind of size. The biggest one we've seen so far was 80 kilometers in diameter, but they can also just be a couple hundred. So they're super small. They're made of ice and dust. If you've ever been to Rosetta SWT, you will remember the endless discussions about how much ice and how much dust. So I'm not going to get into it. There's other people that do that much better, and they shout a lot more. They're from the outer solar system, so that basically means that whenever we see a comet coming into this inner solar system where we can observe it with spacecraft, is that it has come from an orbit either starting in the Kuiper belt or in the Oort cloud and has been disturbed somehow. And most of the comets that are on recurring orbits are Jupiter family comets, because they're bound by the gravity of Jupiter. And the reason that people find them interesting, this does not include me, this is not why I find them interesting, but what we write in a proposal is that they're leftovers from solar system formation, right? They were stored in the Kuiper belt, super cold, they weren't changed at all, and so they are really storytellers They tell us what the conditions during formation of the solar system were. As I said, I don't really care about any of those things because I like plasmas. So what is important for me is that they don't have their own magnetic field. Yes, they're too small to have a dynamo, and there's no remnant magnetic fields like you would expect from the crossophers at Mars, for example. And the really important bit that I will come back to again and again, you can kind of see in this image. This is Halley, yes, 1986, or in this image of Halley. You can see these lovely jets, this dust and gas coming out of it. And that's really what makes it interesting from a plasma point of view, is that you're introducing this new medium, these neutral gas molecules into the solar wind. And that's what makes the plasma. I've cheated a little bit. Does anyone know what this is? Yes.
Is that Kuiper belt object? That
Yes, exactly. This is
visited?
This is a Kuiper belt object, but you can see that shape-wise, they look pretty similar, and that's because this is not yet a comet. It might someday become one if it gets disturbed enough. Yeah, millions, billions of years, who knows? But yeah, this is an image from the New Horizons probe. So this is still very far away, but you can clearly see that this might end up like this eventually, if it ever gets into the solar system.
What about ferromagnetism? Does it have iron?
Very little. It's mostly silicates. Okay, so let's talk a little bit more about 67P because that's the comet that we've explored the most due to Rosetta. And so what you will see a lot during my talk is a timeline that starts in August 2014 and ends in October or September 2016. This is because that's the mission time that Rosetta spent at the comet. That's where our data is from. And you can see that Rosetta, it launched in 2004, took 10 years to go out to 3.8 AU to rendezvous with this comet. That was one of the objectives of the mission, was to find the comet when it is still very far from the sun and when the outgassing rate is low. That makes sense. So this year's the outgassing rate. Let's look at the blue line first. This is a model, so it's very smooth and lovely. It has nothing to do with reality. But you can see that as the comet and Rosetta are very far from the sun, the outgassing rate is very low. It's in the 10 to the 25 molecules per second. This is simply because the heat input from the sun is low. Yes. As the comet goes closer, you can see the outgassing rate increase and then decrease again after perihelion, which is in August 2015. This is the blue line's a model. When I do anything with outgassing rates, I usually use the red line. This is very wiggly, and I like wiggly lines, otherwise I wouldn't like magnetic fields. But this is derived from actual in situ data. So this is data from the neutral gas instrument COPS on Rosetta, and we can convert that into an outgassing rate if we're using a model, and I use usually a spherically symmetric model. It's not fantastic, but it's still better than this really long time average, which is the blue line. So whenever I mention outgassing rate, that's usually. And here, just for reference, is roughly the orbit of the comet. We join it somewhere here, and go around. And the mission ends in 2016 because there was not enough sun anymore, not enough power to run the spacecraft, and the decision was made to, I don't want to say crash, but yes, crash it on the nucleus.
To rest.
Yes, very gently land it. Yes, I should also point out, so this is Rosetta. It had a little lambda called Philae. I don't really talk about this because I'm more interested in long time processes, and Philae only ran for a couple of hours. So I mostly use the actual Rosetta data. So mostly what I use is the Rosetta Plasma Consortium, RPC, and we have an ion and electron sensor, ion composition analyzer, a mutual impedance probe, and a Langmuir probe, which give temperatures and densities of the plasma. Then we have LUP and MUG. So the magnetic field comes from MAG, which is these two little squares here. Very close, unfortunately, to the spacecraft. There's a lot of disturbance in our. Right, so let's go through this. Yes, we have measurements. That's fantastic. No one's ever gotten this data set before. All we've had up until then was flybys, a couple of hours. It's nice, but it really only gives you a snapshot. This is the first time that we are actually able to observe a comet develop and then, undevelop. And this is really the holy grail of this data set. The problems are that we only have 1 point measurements. So those of you that like to work with MMS and cluster data, we were so spoiled. We don't have this. We have 1 point and we have to guess everything else. The other issue that we have is that we got a very, very, very negative spacecraft potential. We can go down to minus 20 volts. Yes, this ruins our electron measurements for the low energy ones, especially. And all of our instruments are really hard to calibrate because this is not a spacecraft that was built for plasma. It's a spacecraft that was built for the camera. Yeah, which was a fantastic instrument too. It would have been nice to have a little bit more support. But yeah, that's what we get. That's what we live with. So this is again the comet's heliocentric distance in red, and then you can see in blue the radial distance of the spacecraft to the comet nucleus. Right, and you can see at the beginning we come in here from millions of kilometers and go down to about 100 kilometers. There's a very slow approach. This was to map the surface to find a landing space for Philae. And here you have the Philae landing. And then there's other stuff going on, but the really important bits are maybe what I've marked here by an arrow. So we have a close flyby. This is the only time we really get a radial profile. So at all other times, Rosetta is just sitting there. It's a very slow spacecraft. It moves with 1 meter per second, roughly. It's terrible, yeah. If anything in the plasma moves, it's faster than 1 meter per second, so we can really see Rosetta as a stationary observer. Except for this 2 days here. We tried to do the same thing again because this was really good. Unfortunately, that led to a safe mode in the spacecraft because of this. It's an absolutely lovely image that someone on Twitter, when he's still nice, made. And you can really nicely see the stars moving in the background. You can see a cliff face on the comet. And everything else moving in this is dust. Yes, so Rosetta navigates by sight. It has 2 cameras, 2 navigational cameras, and it basically star tracks, has 2 star trackers and the navigational cameras. It tries to find the comet and it tries to track the stars. And if one of them fails, it goes into safe mode. And in this case, you can very clearly see and so in this case, Rosetta flew too far into this really dusty environment, lost track, got really confused and went to safe mode, which brings it to 400 kilometers and basically makes it cry for help. Yes. And that scared everyone in ops. The Darmstadt people were very scared for the day. They almost lost their really expensive spacecraft. Anyway, that made them really cautious. We weren't allowed to go that close again until after perihelion. It's a bit sad because the close environment is really interesting. What we did get was a dayside excursion. So this is the furthest point that Rosetta ever went. It was 1,500 kilometers. Not very far, considering that the environment can get as big as millions. So we really didn't leave the inner coma at all. And we got a night side excursion, which went down the tail, but only the really close tail. If you imagine these lovely images of tails being swept away in the solar wind, we got nowhere near that. Yes, we're still in the inner pixel. And then at the end, we were allowed to get close, but by then the comets had become so inactive that a lot of the structures that we were interested in, like the bow shock and the diamagnetic cavity, were no longer there. One thing that I want to stress here is that because of this really cautionary approach that was really dictated by the dust environment, from a plasma point of view, we never really crossed into different regions, because every time the plasma environment and the dust environment expands, the spacecraft goes further away. If it contracts, the spacecraft comes closer. And this is really problematic because it basically means that we don't get to explore different regions at all. We will see that soon.
Sorry, what was the size scale of the movie on the left?
This is a couple hundred meters, I think.
Couple of 100 meters.
It's a cliff face.
Uh-huh.
You can kind of see, so this is the vertical bit, and you can kind of see it has collapsed a little bit at the bottom. Yeah, I mean, there's people that just look at these images and try to find surface changes. Absolutely incredible data set. Anyway, right, we come back to Cyril. All his fault. This is from his paper. So we have a gas production rate. The gas production rate produces gas, neutral. Now we're interested in the plasma, which means we need to make the plasma. And there's different mechanisms that do this. So we have our water gas, and it's split up in H2O plus ions and electrons. And most of the time we do this with the gray line, which is photoionization. Yes. The closer we're to the sun, the higher that rate is. If we're far away, it gets a bit lower. However, unexpectedly, electron impact ionization is also really important, particularly at the lower gas production rates. We also have charge exchange and impact ionization, but they play a minor role most of the time. When I do any modeling, I usually only look at the photoionization because the electron impact ionization is incredibly difficult to predict. You need very good measurements of the electron environment, which we don't have. We have some ideas, but you also need very good measurements of the electron environment in the kind of line of sight. And we have 1 point. Yes. So most of the time, especially when I'm looking at stuff near perihelion, all I do is take photoionization into account, and that usually works quite well. But there's some very nice papers by Marina Gallant and her group who really look at this, and they can really lovely predict the impact that this extra process has and how much plasma it generates. And if you look really carefully, you can even see aurora on this comet. EUV emissions from accelerated electrons falling into the potential well around the comet, which you can discuss if it's aurora or not. I think it is. It's close enough, and emit nature. That helps. But you've seen this before. This is the gas production rate. So that's one side of the equation. The other side of the equation is always the solar wind. So this is what the solar wind looks like at the comet during the mission. You can see the magnetic field, Parker angle, density, and velocity. And the 3 different colors are 3 different models. Yes. Big problem is that we don't really know what the solar wind does at the comet. We have no idea. There's no solar wind monitor, and most of the time the comet is so far away from Earth that we can't even use propagation models. Yeah, they're all pretty bad. So most of the time, what we're trying to do is we're trying to guess in the dark. Sometimes we're lucky and we get a CME that we know what it looks like. Or maybe it crossed Mars afterwards and we can use some Mars data. But really, most of the time, we're just guessing. And that's a big problem because we know one side, we don't know the other side, and then we're trying to place our measurements somewhere in that. And that's why simulations are quite important. Right. So what happens? So you have the comet on one side, cometary plasma. The nucleus doesn't really matter for the plasma at all. It's too tiny. Yes. The cometary plasma is very slow. The neutral outgassing velocity is roughly 1 kilometer per second, most of the time lower. And on the other side, we have the solar wind, which with its magnetic field, really, really fast, but only protons. Yes. So the mass difference between these is a factor of 18. So really, when we're looking at cometary physics, cometary plasma physics, the main question we ask every time and that we break down is, how can we incorporate these cometary ions into the solar wind flow? Because even at Caesar's times, they knew that tails exist. So we know that these eventually have to be as fast as the solar wind. We just don't really understand how they get there. And that's kind of what we're trying to achieve when we look at the data. It's the only equation, I think. Well, yeah, the plasma physicists, you should all know this, right? This is the MHD equations. This is mass conservation law. You have time derivative, you have a convective derivative. And usually what you do is you set this side to 0 because you say, oh, we don't have a mass source. The comet does have a very big mass source, and that's how we incorporate it. So in a very, very fundamental and very simplistic view, this is how you can solve the question, right? This is how they're being incorporated. You basically treat the environment as a flow of plasma, and you say, oh, there's a mass source. And you solve the equations, that's possible, and you get a result which gives you a deceleration of the flow due to the added mass. And that works roughly within 1 or 2 orders of magnitude, but it's not perfect. There are some assumptions here that are not particularly true. So, for example, this assumes that as soon as we create a cometary ion, it is immediately accelerated to 400 kilometers per second. This is obviously not true. There's an acceleration timescale. But it's at least a start, yes? The important bit that we need to realize here is that even though the comet is 4 kilometers big, because some of the cometary neutrals will only be ionized millions of kilometers into the solar wind flow, we already start mass loading millions of kilometers in front of the comet. Yes, and this is really important because that means that our interaction region can be millions of kilometers. This makes simulations really, well, the box needs to be ginormous. Well, yeah. The other thing is, I keep talking about the magnetic field. Technically, this is a gas. There's no MHD in this. What I've written down here. So you just go, it's frozen in like induction equation, whatever. And then you get a magnetic field out of it. And the most important bit is that you see the magnetic field pile up. Yes. So the solar wind approaches, the magnetic field is low. As it slows down, the field lines get compressed. And you get high field. So that's what we call a pile-up. If you do it in 2D, you see draping. So the magnetic field lines going around the nucleus. It's very similar to what you see in the magnetosphere. The other problem that we have, and that will become very important in the study that I'm showing later on, is that in this fluid approximation, you're not taking into account that the ions are actually not really fluid. We're very, very close to a kinetic ion regime here, or even in a very much kinetic ion regime. And this are some simulations by Jan Dekker. These are actually fully kinetic, so the electrons are also kinetic in this one. However, I just really like this picture. But the really important bit is that if we can't, these H2O plus ions, because they are so heavy, because the magnetic field in the solar wind is just 1, 2, 3 nanotesla, they have a really big gyro radius. It can be 10 to the 5 kilometers, 10,000, 20,000 kilometers. And this is obviously much bigger than the point where all of the ions are made. And so we do need to take that into account. And we can actually see this in the data very nicely. So when you look at the configuration in the solar wind, you have the velocity in one direction and you have a magnetic field. And that makes a convective electric field. And these these cometary ions will then be accelerated by the convective electric field. And if you remember your fundamental plasma physics lecture, they make a gyration or a cycloid if there's a drift. And this is exactly what we see here. So in this simulations, these are the density of the cometary ions, and you can see them all being picked up here and going in this direction and starting a cycloid that goes down here. And this is in no way reflected in the MHD model, right? So while the MHD model gives you a really good feel of what happens on ground, once you dig deeper into it, you will already find a really fundamental deviation from this. And this can lead to really fascinating phenomena that I will talk about later on. Okay, so this is I think my last slide of the introduction. This is, if you remember the gas production rate from the beginning. This is only 1/2 of the mission. This is the first encounter, and perihelion is here. So low gas production rate, high gas production rate, or we also call it activity. And the really interesting thing is that this environment around a comet, depending on gas production rates, can have wildly different shapes and wildly different processes. So, for example, these pickup cometary ions, the ones that are being picked up by the convective electric field, they're particularly visible when the outgassing rate is low. So at low activity, because we have no shielding of this convective electric field. Once we start producing more ions further away, we can actually shield the convective electric field from the inner coma and prevent the ions there from being picked up. So suddenly we create something entirely different in the inner coma. We also have different wave regimes. So Martin, I'm sure, has talked here about the singing comet waves. So those only exist at low gas production rate because you need this convective electric field to produce them, we think. The auroral emissions can also only exist at that stage because only then do you have this acceleration of the electrons towards the unprotected cometary nucleus. Once we go to higher outgassing rates, the solar wind ions get deflected, right? So everyone remembers momentum conservation, yes? Cometary ions go up, momentum has to be conserved, so other ions have to go down, and the only other ions that are left are solar wind ions, yes? While the cometary ions move upwards in this image, the solar wind ions will move downwards. And this is something we can see very well in data. It also means that these singing comet waves disappear because their driver is no longer there. And then this is the high activity case, and I'm going to make it big because that's really what I'm going to talk about today. This is the fully formed comet. This is the image that people had in 1986, because this is the regime that Halley was in. Yes, Halley is a very active comet. Its gas production rate is 10 to the 30 or above. The highest 67P ever got was 10 to the 29th, but this is still the closest it got to the Halley state. And you can see that we form a bow shock. Yeah, so this is where we can talk about if you load a fluid enough, it will eventually form a bow shock. And then we have the draping of the magnetic field lines. And in the middle here, that's the diamagnetic cavity. And it's called that because there's no magnetic field in it. So I'm going to show data later on, and you can see there's clearly no magnetic field fluctuations, and we think the magnetic field is also zero. We knew this existed because Halley and Giotto detected it. We also see the cometary ions expanding radially outward without any hindrance, no convective electric field, because there's no solar winds anymore. And so this regime is entirely different. And really we're dealing with, this comet has multiple personalities in terms of the plasma, right? It can change from one to the next within hours. And that makes it really interesting and really difficult. One thing I want to point out is that we have this thing called the solar wind ion cavity. This is not diamagnetic cavity, they're different. But But this is something that was it was kind of forgotten about at Halley. It existed, but it was really hard to measure because the instrument broke. But at 67p, we were able to measure the solar ion cavity quite a lot. And basically what happens is that the solar wind ions that are deflected because of the momentum conservation dive below the comet, and they can't go past this point, which we've termed the solar wind ion cavity boundary name, but it's very accurate. And basically that means that in this region here, there's no solar wind ions anymore. They've all been deflected. Now you could ask, but there's no solar wind ions. Why is there a solar wind magnetic field? That's because the electrons can still contribute. Yes, with electrons, it's always a bit hard to say where they come from because you can't really paint them and track them. And you kind of go off of, oh, this energy is one population and this energy is another. So we're pretty sure that the solar wind ions, they do continue and they carry the electric field. And then they're being neutralized by the picked up cometary ions, the ones that have been picked up here. They've been accelerated already, and they continue to go inwards instead of the solar wind ions. So we already have a really good momentum transfer between the cometary and the solar wind ions upstream of this. And you can see very nicely in the data that there is an accelerated cometary ion population and a newborn cometary ion population. Right, if we then go further inwards, this is the diamagnetic cavity, and this is just characterized by the magnetic field going to zero. And I want to talk a little bit more about what we know about this. So, 1986, Giotto. There's a magnetometer on that. Lovely. Really nice. Oh, really nice observations. It saw the diamagnetic cavity. It basically flew through it here. So this big circle is the diamagnetic cavity. Flew through here, and everyone jumped and went like, "Ooh, let's explain why it's here. What makes the diamagnetic?" And people very quickly came to the conclusion that it couldn't be thermal pressure, because the thermal pressure inside of this diamagnetic cavity from the electrons was, one, very small, because they're very cold electrons, and two, not different from the one outside. The electron population doesn't change much compared to inside and outside. So it's not thermal pressure, it's not electrons pushing outward. So the predominant model, I think we should say, at that time was developed in 1986 and 1987 by Tom Cravens, and he said it's ion neutral collisions. Yes. So basically what happens is we have the magnetic field coming in on this side, accompanied by ions, cometary ions, and where the diamagnetic cavity boundary is where the cometary ions are colliding with the cometary neutrals, and every time they go this way, and every time they collide, and they go, collide, go. And so if the cometary ions can't go on, the magnetic field can't go on. And people are like, yeah, that sounds plausible. They developed this model. It predicted the correct distance for the diamagnetic cavity boundary, roughly 5,000 kilometers. And they were like, yeah, that's it, done, all explained. Yeah. I'm not going to talk about the validity of that model and what I think is wrong with it. I'm going to talk about why I think we can't use it for 67. The first bit is the inertial lengths at 67p are wildly different. So we go back here. We're talking about ion neutral collisions. What did I say before, though? Before I said that the ions and electrons decouple, and the magnetic field is actually coupled to the electron. So we're kind of doing the electron and HT kind of situation. So this whole, oh, if the ions stop, the magnetic field stops, is already pretty questionable in this scale. Yeah, and you can see this very nicely in the inertial lengths, which are plotted here. So Rosetta, and this is the distance from the nucleus. This is the inertial length of the ions. And you can see for Halley that the Giotto spacecraft never came anywhere near any of the inertial length scales, either for the electrons or the ions. However, if we look for 67P, we're very, very, very close to the ion inertial length. Yes, and that's simply tells us that they probably decoupled anyway. So ions probably don't matter so much. The other problem that we have is that for this model to work, what we see is, we say ion-neutral collisions, but basically what happens is a charge exchange reaction, I think. And Sarah can correct me if that's wrong. There's some weird nuances with these things. But basically, the ion will move here, it comes with a magnetic field, it collides with a neutral, and they exchange an electron. So now our fast ion is a neutral, still fast, but we don't care because we care about plasmas. And what we've created is a really slow ion that moves with a neutral velocity because it's just been created. So if this ion-neutral collisions were effective, all of our ions would be at the neutral velocity. We definitely don't see that. So this is from Elias Oderstadt's paper, and he looked at the ion velocities. This is many measurements, a histogram. The neutral velocity is here. The peak of this distribution is much higher. So our ions are actually much faster than the neutrals, which means that the ion-neutral collisions don't couple very well. Yes. So this whole Craven's model might have applied at Halley, but at 67P, because it has a lower outgassing rate, it doesn't matter. What this also tells us is that these ions have to have been accelerated somehow, and that means there is some transport. So for the Craven's model, they assumed that there's chemical equilibrium. Basically, you create an ion, it sits there, and once it starts accelerating, it immediately gets removed by recombination. So it gets made an ion, gets made a neutral, so it's no longer there. So it never gets to the point where it can actually be accelerated by a field, by electric field or whatever. So no chemical equilibrium, which means we have transport, and no ion-neutral collisions, or very negligible ones. And that means that this whole model doesn't work at 6 eon. Okay, this is my favorite. I'm going to talk about fun facts first, and then I'm going to come back to the model. So what else do we know about this diamagnetic cavity? So a very recent paper came out by Zoe Lewis, who's at and she ran simulations, fantastically complicated, but one of the results was that you can actually see that there has to be an ambipolar electric field. So an electric field that points from the nucleus out towards wherever, yeah, it's a radial ambipolar. This ambipolar field is what moves this peak from an ion starting at neutral velocities to an ion being accelerated. Yeah, so at least we can explain why our ions are so fast. And she actually found that most of the observations can be explained if we include a 1/r profile. The other thing that we learn about the ions is, so this is magnetic field measurements from the cavity. Yes, I don't think I need to tell you where it is. It's very obvious. A bit in the middle, no field, no fluctuations, nothing. But what you can also see is outside we have these steepened waves. They're ubiquitous. We see them everywhere near the diamagnetic cavity. And this is from a paper written by Rashka Mahajra, and he actually found some instances where these steepened waves managed to penetrate the diamagnetic cavity as ion acoustic waves. So what we have is some sort of magnetosonic waves outside, and then the ions convert them into ion acoustic waves that can penetrate this. This also tells us that this boundary for the diamagnetic cavity doesn't really seem to care about the ions. The ions are pretty, they can just go through it, doesn't care. They're not being changed by it, which makes sense because their gyro radius is much bigger than the diamagnetic cavity itself. However, What does care about it is the electrons. And so this is from a Medallion paper, and you can see pitch angle distributions of electrons. And they're basically, this is the electron spectra, this is the magnetic field, the diamagnetic cavity is here. And just looking at the colors here, you can tell that there's something different. And basically what happens is that the electrons with a certain pitch angle, they're expelled. So they do stop at the diamagnetic cavity boundary. Ions continue, some electrons stop. And you can actually see that they're being rerouted to follow the magnetic field, so they become parallel field-aligned currents here. Ions don't matter, electrons do. Another thing that we found about electrons is that they're collisional where the diamagnetic cavity is. So Pierre and I, so Pierre-Henri, who wrote this paper, had a fantastic idea about developing a model, and we did, and then it didn't work out. And this is the part in the presentation where I go, I don't know. I don't think we understand what else is going on. We know what's not going on. It's not ion-neutral collisions. It has to have something to do with the electrodes, but what exactly? Yeah, so this is my palette cleanser before I go to this fun bit, the bit that works. So I know you have mountains here. We have hills. The biggest one is 800 meters. It has a few centimeters of snow currently. You can't ski on them, they're too flat. But they're beautiful, so do come and visit us. Northumberland's really nice. Also, next time your meeting wasn't an email, consider if it should have been a duel. I have a stick already. Okay. So, I'm going to go very quickly through this bit. But I want to talk about one thing that we actually do understand, and it's really nice. Yes. So, let's go back to this. Here, very far away from the comet, we have a magnetic field, we have solar wind ions. We move into the solar wind ion cavity I talked about before. Solar wind ions are gone, magnetic field remains. We move even further, no solar wind, no magnetic field. This is the default situation. Now, this is 67p, and it never listens to anything. It makes chaos. And so this is what we usually measure. This is the diamagnetic cavity measurement, magnetic field down here, ion spectra here, and you can see there's not really much going on, especially in this one. And this is the solar wind ion spectra. Now this is fine. Now we don't expect any solar wind ions there because they're outside of the ion cavity. We should never get this far until they do. Right there. Yes. Diamagnetic cavity, these are the cometary ions, and you have solar wind ions. And no one knows where they came from. They shouldn't be there. They're really fast. Oh, no idea. And so we wrote a paper about them because we found it really interesting. There's only 5 instances where we saw them. And we were like, well, why are they there? So we looked at when these 5 instances occur, and they occur at low gas production rates and only very close to the comet. So these are, the blue points are all the diamagnetic cavities that we found, over 700. And the 5 are all down here. Yes. Low gas production rate. We also found that the velocities of these ions indicate that they're coming straight from the sun and they've barely been decelerated or deflected. So it seems like they didn't even notice the comet was there. Bit rude, really. So, how can this happen? And really what we need is a situation where the solar wind ion is not deflected, where it ignores the comet, and the diamagnetic cavity needs to expand, because remember when I said the spacecraft doesn't move? It doesn't move. So when we see a diamagnetic cavity, that really means that it has to be small. The spacecraft sits here, it expands, we measure it, and it contracts, we don't know. So that we need to explain, and that's actually a combination that's really hard. We ruled out a couple things. We ruled out solar wind cause. We ruled out a neutral gas cause. Then we went to Cyril. We were like, help. And he suggested 2-time charge exchange. This has been observed at Mars. You can see very nicely. But my student, Lucy, made some calculations with Cyril's help. Even considering how much uncertainty we have, nowhere near enough. And that leaves us with one explanation. And that's that the solar wind velocity and the magnetic field are parallel. What does that mean? It means the convective electric field's gone. Right-hand rule. If these are parallel, no field. It also means we don't have any deflection, because no convective electric field means we can't accelerate our cometary ions, which means we can't, in conservation, deflect solar wind ions. It all works. And we don't really have data for this. There's one simulation that basically tells us by Christoph Kenders from even before Rosetta arrived at the comet, but he predicted that the smaller the angle between these two is, the smaller the mass flooding efficiency. So this works. We can explain no deflection. Can we explain that the diamagnetic cavity expands? Even harder. But there's one simulation by Thomas Cambosi from 1994, where they put the magnetic field parallel to the velocity. And what they see is that in this pileup region, there's no pileup, because you can't pile up the field along the field. Yes, divergences. So the green line here is the usual situation where they have an angle between them. You see this lovely pileup, the field strength is higher. And in this case, it's much lower, which means that we have a lower magnetic pressure. So there's less pressure from the outside, which makes the cavity expand. And so this is roughly what it looks like. Normal case. In the strange case, the solar wind ions just ignore the comet because they don't know about it. There's no electric field that can convey the information. And we ran some simulations. Herbert did that, I didn't. And this is the normal case. Yeah, this is roughly what it looked like in all my sketches, except the sun is on the other side now. And this is the parallel field case, and you can see that all of these structures just vanish. And the important bit here, though, is that this is still blue. So there is still a diamagnetic cavity, but there is no other structure. And so you can see here that the proton density is pretty much unchanged until you get to the wake. So that's a bit like the moon. I'm going to skip this because I've run out of time and say Picard approves. For once, the data and the simulations agree, and we think we're right when we say this is what causes the protons to appear. And then we submitted the paper, and the next day we found this. And it's exactly the same thing happening at Mars. Mars and Venus are the closest to comets that we find in the planetary realm because they don't have global fields. And you can see this is the parallel fields version, and there's also weird wave activity, which we didn't look at, but you can also see that the solar wind can penetrate deep into the ionosphere, which it usually can't in this case. And then a couple months later, you found this. This is actually the same thing at Venus. Yeah. So this seems to be a thing that exists at all of these bodies that don't have their own internal magnetic fields, where radial alignment of the field and the solar wind velocity can just completely change the behavior of the environment. And it's just really nice to see that the physics are the same at all three things. This is where I will stop. So Rosetta is using the compass. So what do you need to remember after this? So comets are super interesting. Their plasma environment is dynamic, and whatever you're interested in, you can probably find it. If you like waves, look here, we have lots. Right? If you like reconnection, we don't actually know if it's there, but maybe. People say tail disconnections are made by reconnection. Dipolarization fronts, who knows? There's a tail, it has a current sheet. But we don't understand most of our data. And the data that we do understand actually seems to be nicely fitted with the Mars and Venus data. And it offers a new way to look at this interaction without going back to the spherical cow in a vacuum, which is always field and velocity. And for those that are a bit disappointed that I didn't answer any questions, I just want to say that Comet Interceptor is coming. It will answer some of these. It will not answer all, and it will probably make more questions. So I'm really excited about it. And I just saw the electronics board, and it seems to work, and it'll be good. So I'm back in 10 years.
Very much, Charlotte. Any questions? Hans.
You've mentioned that the spacecraft potential is negative, but to do photoionization, shouldn't be the spacecraft potential positive?
Yes, but we also have really cold electrons and really weird environment. No, actually, no, we have really hot electrons. That was the problem. So all of the electrons really love attaching themselves to the spacecraft for some reason. The Frederick Johansson ran many specifications, and it turns out that there's also some surfaces on the solar panels that don't help conduct very.
And the solar panels are huge.
Yes.
It's like 10 meters.
Surfaces don't.
10 meters per object. Peter.
I wanted to ask about the photoionization of water, because its brother is photodissociation. So you should also get OH and He. I think you cannot have just one of them.
Yeah.
So if you would consider that, would it change anything? I mean, say you would have a cascade of having OH, and then you can ionize OH, but then you can also produce O, and you can ionize O, etc., all with photons. Is that changing anything, or is it the same?
Right. So this is very good, because if you're looking at tails of comets, you see all of those ions, right? The problem is, because we're so close to the nucleus, most of those reactions haven't happened yet, because their reaction rates are quite low. And because we're literally just seconds away from them being born, the only reaction that's really happened is water ionization. Or if you're really far away from the sun, actually, it's CO2 that's being ionized, because that's the predominant. But yes, those happen. And in Zoe's simulations, she actually sees that H3O plus is being generated at high gas production rates. And at Halley, H3O plus is the dominant ion. 67p, most of the time it's H2.
But it doesn't change the plasma dynamics. No. Okay, thanks.
Because those ions are all very small.
Christian.
I have two questions, if I may. So you said at the very beginning that the propagation models of the solar wind, or solar wind propagation models, are very unreliable at the position of the comet. Why is that? Because I mean, to me, it looks like it becomes even easier, but apparently not.
No, so first of all, it's very far away radially. Most of the time we're 2 AU, 3 AU, 4 AU away. Yeah. And the other problem is that the solar, so if the sun's in the middle, Earth is here, and the comet's here. So all of the solar wind that goes here, we never see. Right. So you see the Parker spiral arrive eventually, but that takes a very long time. And by then the propagation models have a huge time uncertainty. Some of the structures may come around, but you can see, for example, the heliospheric current sheet. Let's say it's supposed to arrive on day 1 according to the model, but we actually see it in the data on day 4. And that's very common.
Yeah.
And this is obviously not a constant shift, because that would make it too easy.
Oh, right. Okay. And then this is really my understanding. You said that H2O plus has to be as fast as the solar wind. Why is that? Because my understanding was the H2O comes from the comet, and then.
But okay, so when we look at comets using telescopes, we see the tail. So we see the nucleus, but most of the time people love the tail. And because the cometary ions in that tail have been shown to be quite fast, roughly solar wind velocity, because they don't have an aberration angle, we know they have to get there somehow, right? Because we can observe them at high velocities very far down the tail. However, the step between, we don't really understand. Because the highest velocities I think that we see is 100 meters per second, and most of the kilometers per second, and most of them are actually moving in the wrong direction.
They are trapped, right? Sorry, but they are trapped in the field, so you can have this.
Yeah, I mean, I'm not surprised that happened,
It's
right?
not surprising.
Yeah.
It's a trapped.
Yeah, no, it's perfectly understandable, but it still means that we don't understand how we get from one point to the other.
Okay.
Daniel.
Another question on the ionization of the neutral gas. You said that most of it, or modeling, you only account for photoionization. I want to say, ask if you know or can state any ratio, percentage of what you think is due to photoionization compared to electron impact and other effects.
Yes, I can. Sounds like a very nice paper that someone may have written. There, that's it. I'll point at it again. So this, I'd say the biggest difference is probably here. The gray line is photoionization. And then this is the highest electron impact ionization rate. So it's a factor of 10, 15, I would say. Yeah. So it can be very dominant. It's just really difficult.
And in modeling, how do you cope when only accounting for photoionization? Do you just take a greater value for photoionization to account for other processes as well, or?
Yeah, so this really depends on what kind of model you're running. So you can account for electron impact ionization if your model includes electrons. Yes. Or you just blanket take, this is the ionization overall rate that I take. Yeah, that also works. But it really depends on what kind of model you're running. You can do all kinds.
So sometimes you have this convection electric field, non-zero, which means that the velocity and the magnetic field are not aligned. Then the ions are not penetrating inside. And when it is zero, when the velocity and the magnetic field are aligned, then some ions are penetrating. Yeah. The question is if it is the property of the solar wind or the solar wind interaction with the comets. If it is the property of the solar wind that the solar wind is generating the alignment between velocity and magnetic field, then you can study the solar wind and its radial evolution anywhere. Yes. Okay, and then you can speculate what is happening at different radial distances from the sun, with the known statistics of VB alignment.
Yes, we actually talked about this just before.
Okay.
Yeah.
Good question.
Yeah, because I guess the closer you go to the sun, the more of these radial fields you should have. But we don't have a spacecraft that close to the sun near a comet. So you might have to use other means to look at this. See, you might have an idea.
Yeah, maybe.
Could you go to the page before the conclusion? According to the alignment, this kind of study, right? I think all this study, Mars and Venus, is follow up our paper in 2009 or 2010. And there's two extreme situations.
Yes.
Parallel and perpendicular to the solar wind. And we have two cases, and we did the MHD simulation, if you have ever seen that paper. MHD simulation. You see one case.
For Venus or?
Yeah, for Venus. Yes. And one case, you don't have induced magnetosphere at all. Yes. Another case. Then the title of the paper read implication to the stellar wind interaction with hot Jupiter. Because for the hot Jupiter, at that time, stellar wind must be, if the magnetic field from stellar wind must be parallel aligned. So that interaction must be similar like
Similar to that.
this situation. But there's a lots of papers
Yeah.
on this extreme situation,
Yes,
parallel perpendicular. And the Venus easy to find this case.
because it's so close.
Yeah.
Yes, yeah.
In this case, we have lots of works on that.
I think the reason why this one stood out was.
First, this is just all the follow-up paper. We have the first one.
Yeah.
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 Yeah, no, I think the reason why this one stood out was that it had a very similar, it was talking about the solar wind ions
Mhm.
specifically, and that's what we were looking for, which is why I chose these two papers. But yeah, I mean, in hindsight, it makes total sense that the angle between the solar winds and the magnetic field would be really important. But yeah, it took us a while to get there.
Yeah, and these changes at Mars and Venus, they can be quite fast as well.
Mhm.
So the time scales on how long those processes sort of how long they take place.
Yeah, I mean, in this you can see it's within minutes that it changes back, right? Because here we already have an interval where we don't see any photons anymore, right? So minutes, it doesn't last longer than.
And there is also a recent paper in Nature, I think, by
Yes.
that's the team
Simulation, it's based on simulation.
Yeah, exactly.
We did the simulation 15 years ago, but still.
These ones are hybrid simulations, so it's complementary, right? But I don't know if
We did on the MHD,
MHD, yes, and
UCLA model.
right. And Stas, I think they did it with hybrid simulations.
Mhm.
So it's a slight complementary, I think, aspect to it. But I don't know if they actually
I know
quoted you or not.
Yes, in the supplement material.
So the
Otherwise, because we have the result already.
switching forth and back on Mars and Venus, is it also on the order of minutes or?
It is quite fast. I think that one of the prevailing ideas is that it was in a matter of, I would say maybe closer to hours, maybe, or a little bit less.
Because this has an implications of the chemistry, right?
Right.
If it's closer to hours, okay, everything has equilibrated. But if it's on orders of minutes, then becomes questionable.
Yeah, absolutely.
I mean, I think it makes sense that it doesn't last very long here because the environment's so small at that point.
Oh, yeah.
So the solar wind has probably gone through it in its entirety in seconds.
Yeah.
It's very fast.
Yes.
Maybe a naive question, but you showed that there's a radial electric field. And from the engineer's perspective, I would expect, okay, that means the inside has a higher potential than the outside. And that's also what I would expect, that the comet is charged in a way relative to its environment, the overall. So
Yeah.
wouldn't the particles, dust and water that come from the comet also be at least partially charged? Has that an impact? Or?
So there's always studies about this. And okay, so the first thing is the electric field that we see is super small. So it doesn't really do anything with the dust particles because the charge is so small. Does it in total affect the dust? Maybe, but it doesn't have a visible impact on the dust distribution. Because the dust too heavy, field's too small.
Can I have a last very silly question?
One last question.
If you have so much dust, why doesn't the dust kind of wipe up all the charges in the environment?
This is a very good question because there is a really nice paper that in 2011 or 13 or something that said, oh, there's so much charged dust in this environment. And then we got there and there wasn't. And the theory is that the dust particles are too big at that point, and the electrons are too cold or too hot. One of the two. Yeah. So there's a paper by Erik Wiegren who reran his simulations from before Rosetta, after Rosetta, with the actual real dust size distribution and the real electron energy distribution, and he then finds that there isn't a lot of dust charging.
And in the upcoming Comet 3 book,
Yes.
will be
It's a chapter.
we have like a chapter about that. So Arnaud Bett was in charge of the chapter. talk about a little bit dust as well. So it's more like a review of all the observations we had with, yeah, like from the plasma point of view, dusty plasma. Okay, so we'd like to thank our speaker again, and thank you for coming today.